And, or yeah, chapter 15, because we're going out of order. And that's all about acids and bases. And you guys already know a good bit about acids and bases because they're one of those common substances that we've run across, you know, in our reaction on in our chapter on reactions. We've run across them as, you know, reactants and products in various labs. And so we should be a little bit familiar with acids and bases already. What did we define an acid and a base as originally? So how can I recognize an acid in a chemical reaction? Yeah, so we said that acids have an H in front of them, and we said that bases are something plus an OH minus, and we said that this is generally a non-metal, and that this is generally a metal. And what that really is simply the most basic definition of an acid and a base, which is due to Arrhenius. Why should we remember him also, aside from his definition of acids and bases? Actually, let's do it this way. Scientists from chapter 1, famous for discovering that substances, when dissolved in water, can conduct electricity because they form cations and anions. And he decided that you don't necessarily need water to do that, or water to do that in, meaning you can do it with pure molten chloride. So that's from chapter, gosh, now I forget. Was that, what scientist, was that chapter 5? 5. So, good review for chapter 5 test, or the final about chapter 5. And what he basically did is he simply said, acids are anything that gives excess H pluses when dissolved in solution. And then bases were anything that gave an excess of OH minus when dissolved in solution. So really his definition is probably what I would say 99% of people think of as acids and bases. And it probably is the definition that is best suited for us. And we can rephrase his definition in a slightly different way. What he's basically saying is that if I've got a solution with more H plus than OH minus, I'm going to call that an acid. If I've got a solution where the concentration of H plus is equal to the concentration of OH minus, I'm going to call that neutral. And of course, mathematically, the last combination is if I have more OH minus than H plus in solution, we're going to call that a basic solution. And based on his definitions, we know the most common acids. There was 10 of them, right? Does anyone remember all 10? I'm not going to put the names down, I'll just put the chemicals. It's good practice for the final. Iodic acid, sorry, just iodic acid. Because it's iodide, iodic. And Br would be called bromic. We had acetic. Someone said someone in there that I missed too. Nitric acid. What is that? 1, 2, 3, 4, 5, 6, 7, 8. We need 2 more. This is tough. And carbonic. And what did we say for bases? Yep, basically, bases basically get it anyway. I use that word way too much anyway, I realize. It's basically any alkali or alkaline earth metal. Plus OH, although arguably it can be any metal plus that. We said the most common one is probably sodium hydroxide that we use 99% of the time. Potassium hydroxide, magnesium hydroxide, and calcium hydroxide are probably the four most common ones. So that's a pretty good definition of acids and bases. It gets us probably 95% of what we really want. But there's two more definitions that we're going to talk about. The second one we'll probably use a bit frequently, and then the third one is kind of academic, meaning we'll talk about it and we won't use it so much. But I still want you to know it so that when you go forward in the future, you might be able to use it. We ready to go to a new slide, or are we still writing down acids and bases? Okay, we'll just hold up for a minute. Good to go? Okay, the next set of definitions we're going to talk about are Bronsted-Lowry. And they define an acid in essentially the same way that Lewis did, except they used a different word, and we'll talk about it what it means in a second. They basically said it's a proton donor. And what we mean by proton is simply an H+ ion. And so notice that Arrhenius and Lewis's definition of acids acids are the same, meaning Arrhenius said it's in excess of H+ ions. Bronsted-Lowry is saying it's a proton donor in a chemical reaction, but a proton is really just an H+ ion. And if you think about it, it makes sense, because remember, what does H look like? So there's H, it's got one electron, right? If I write H+, it really is just a bare proton, since it doesn't have an electron around it. And so remember, we always talk about hydrogen being the exception to a lot of rules. Well, one of the reasons it's the exception to a lot of rules is that it's the only element with one electron, and so it's the only element that can actually look like mostly a bare proton or a plus charge, essentially. For bases, he changed his definition up. He said it doesn't have anything necessarily to do with OH-, it's simply something that's a proton acceptor. And what that means, though, is that OH- is a proton acceptor. So it still has all the bases that normally Arrhenius had defined, but it now allows us to define some additional bases, or to think of things in an additional way. So if we think about it, you know, if I've got H+ plus an OH, well, let's just do it this way. If I have HCl plus NaOH, those are my most common bases and acids. Well, notice that what really happening is that H+ is being donated, right, to water. Or you can think about it as being donated to the OH-. And notice that that OH- accepts it. And so we get NaCl is our other product, and more importantly, we get water, or HOH, where, you know, this was accepted, or donated, I should say, and this accepted it. The other one that it kind of allows us to do, or to think about, is we can throw water into the mix. Now this looks like a weird reaction, and notice that I am also writing it as an equilibrium, right? And it turns out that water is both an acid and a base. I think it's interesting how chemistry evolves, or maybe evolve is the wrong word, but how chemistry sort of, all these weird little things have to come together to make everything work in the long run. For instance, our definition of acids and bases come from H+ and OH-. Well, water just happens to be composed of H+ and OH-, And so that makes water one of those very rare molecules that is both an acid and a base. So for instance, if this one is considered the acid and this one is considered the base, then what's going to happen is this is going to donate a proton. And we get something that looks like H3O plus OH minus on the other side. It's okay if we do things out of order, I don't mind. And so notice that we have a special name for this. This is sometimes called a hydronium ion. And notice that it only exists in solution. Remember, one of the things we've said since the beginning of chemistry is you can't have anything that's positive or anything that's a negative charge bottled up and stored someplace, that they're too reactive. But that we can have plus and minus charges, you know, if they're in a solution or something. And so a hydronium ion is only formed in water. You can't bottle it up and say I have a bottle of just hydronium ions. But water really looks like that, meaning water really is constantly breaking apart and reforming. And if you think about it, that kind of makes sense, because one of the things we know about water is it likes to form hydrogen bonds, right? And so what we're really saying for this reaction, if I think about it, is that if this hydrogen bond here kind of becomes strong, meaning that when we redraw it, we say, okay, not only is it a partial positive and a partial negative charge that those electrons are attracted to each other, but that sometimes that hydrogen ion actually literally just pops off, you know, and is attached to that oxygen ion. And then, of course, that leaves the other part being simply that OH minus, and this, of course, has to have a plus charge overall. I guess if we're drawing Lewis structures, I better put them in brackets. They're ugly brackets, but that's okay. Yeah, those are ugly. That's okay. So the Bronsted-Lowry definition gets us some additional acids and bases in that now I can have water be both an acid and a base. The last one that we want to talk about, whoa, we are woeing. Jess, how's your truck doing?
Still don't know yet. Let me tell you, it makes it a pain to try and feed horses.
I was going to say, if you need a ride out to go feed horses or something, let me know. Although I went out and fed Melanie's 2 horses yesterday, and oh my God, is it cold out. My fingers were so numb by the end of it. -10, well, it was -10 this morning. It was -20 yesterday morning. Whew. Evil.
That just means you don't need to be doing that.
I'm glad I sold my horse. I'm a fair weather horse fan right now. So the last one is what we call Lewis acids and bases, and this is the same guy from Lewis structures. So again, notice these people kind of crop up over and over again. And what he did is he expanded the definitions of acids and bases to include even more types of compounds, although it still includes all of what we would consider acids and bases from Arrhenius and Bronsted. What he said is that an acid is an electron pair acceptor, and a base is an electron pair donor. Be careful with these definitions. Notice that the Bronsted-Lowry definition is donors and acceptors, and the Lewis acid and base definitions are donors and acceptors. It's really easy to get mixed up which one's donating and which one's accepting. So kind of be careful of those definitions. And what this does is this allows us to think about a lot of chemical reactions that we wouldn't normally think of as acid and base reactions as really being acid and base reactions, because we can think about them in terms of where the electrons are going in a reaction. So if we take a look at that last reaction, you know, when we looked at this actually, remember it kind of started off with that hydrogen bond, right? Well, remember those waters have lone pairs of electrons, right? And so if we think about it, and I'm going to do this in another color so I can emphasize it maybe. assuming this will let me change colors. My computer is slow. If we think about it, this little pair of electrons here is what's going to go and make that bond with hydrogen. And if we think about the pair of electrons that's holding that hydrogen in, that's going to end up on our water molecule when we make it. And so when we take a look at that new molecule, there's the electrons that were accepted. So hydrogen accepts 2 electrons to make a new bond. And then the other part, well, okay, I'll better show this. Plus, and the other part is we're left with an OH, and we've got a lot of extra electrons on that one. This accepted the electrons from that OH bond originally. And so we've got, oh, I'm sorry. Oh, this so I'm sorry, I kind of phrased it wrong. This should be donates. Meaning this molecule donated, this molecule accepted. It's kind of hard to see maybe in this example. I'll throw up another one that's more obvious simply because there's less electrons. Plus, this one's kind of confusing, I got to be honest, to me, always, because it's water plus water, which seems like a weird reaction to me always. Okay, so can I go on to a new one or wait a second? Yeah, I know this. I remembered that. There was a lone pair extra over here that I should have put in. But we weren't worrying about them at that point too much. So notice that all 3 definitions have some similarities in them. And that every definition that we go on past Arrhenius, it always includes all the molecules that Arrhenius would have included. And so, I'll be honest, for 99% of what we do, Arrhenius is probably just fine. Simply because that covers 99% of the molecules that we use in class. And the other 2 definitions are good only in that Bronsted-Lowry is nice in that it gives us water as both an acid and a base, and it allows us to use ammonia as an acid, or I'm sorry, a base. And then Lewis is nice because second semester when we start looking at reactions, we can start following those electrons around a little. And we can talk about some reactions that are actually really Lewis acid-base reactions if we really want to. Oksana.
Can you explain again why water is acid and base?
Well, I don't know which picture looks better as far as things, but to me, this one is obvious that this is an H plus donor, right? And this is an H plus acceptor. That was our definition of acids and bases, right? We can also draw it for molecules that aren't nearly as exciting. So if I take a look at this molecule, it violates our octet rule, so don't worry about that too much. Plus ammonia. What we find is that these 2 electrons in ammonia can go to form a new bond between ammonia and boron. So here's my electron pair donor. Here's my electron pair acceptor. This makes this what we would call a Lewis acid. Maybe I should put that, phrase it that way. And this is a Lewis base. And so when we make the final molecule, we make that new bond between boron and nitrogen. And we can consider this really an acid-base reaction. Oops, these weren't hydrogens, these were fluorines in this example. And I guess I'll show all the extra electrons just to make nice, happy Lewis dot structures. Okay, so that's the basics of, God damn it, I need to pick, oops, I swore. Anyway, darn it, I need to pick better, a better word than basic all the time. Or arguably, yeah. I do notice, it's funny when you start taping yourself, or you have students that are annoying and like to point it out. Like last year I had a couple that would always, every time I started saying a specific word, they would be like, no, no. I'm like, oh. But we do tend to use the same vocabulary over and over again, the same transitions, because they're comfortable. So maybe I need to branch out and come up with some new transitions. I don't know. Okay, the next section... Next section is we're going to look at the reactions of both acids and then the reactions of bases. But this is really a review of things you already know. So reactions of acids and bases. Or really what this is if you're good, this is just a review of Chapter 8, meaning there's nothing new that I'm going to teach you right here. Well, nothing too new. So if I take an acid plus a metal, that gives me hydrogen plus an ionic compound. Now, you can memorize that statement if you want, or maybe if we draw the reaction out, we'll see what we mean by it, and we can simply realize that it's something you already know. So if I have, say, H2SO4 plus calcium, that goes to H2 gas plus CaCl2, which is probably aqueous, although I don't have it written down. So, what is that really from Chapter 8?
CL2.
Oh, I'm mixing up my examples. Oops. You're right, I kind of wrote half of one example, half of another. CaSO4, which likely is a solid, actually, in that case. So, what type of reaction is this really, though? Yeah, this is really just a single displacement. So if you know your reactions from Chapter 8, and I got to be honest, you might as well just start reviewing for the final now, meaning go back, learn the reactions in Chapter 8, and don't worry about studying the reactions in Chapter 15 that are going to be on the test, because you already know them. So you already know single displacement reactions, right? What's the only thing we have to worry about for a single displacement reaction that we have to check? Yeah, the activity series. So we need to make sure that calcium is more reactive than hydrogen in this case. And how do we recognize a single displacement reaction? How did you guys know that? Brittany, how did you know, since you said it first, I think? Or loudest? So it's an element plus a compound, right? And in this case, the compound just happens to be an acid, right? Does it have to be an acid? No. But in this chapter, since it's Chapter 15 on acids and bases, it's going to be acids and bases. So, didn't teach you anything new yet. This is boring. Okay, next one. If I take an acid plus a base, I get a ionic salt plus water, and then we always added, since we know this already, heat. Well, what's this just our classic example of? Yeah, it's just an acid-base reaction, right? You know, if I take HCl plus NaOH, I get NaCl plus HOH plus heat. And this is just our classic acid and base reaction. Oops, I wanted to do red just because I can. Classic acid-base reaction. So again, haven't taught you anything new because, well, we learned it in Chapter 8. What else is acid-base reactions really just? They're just a special case of double displacements. Okay, what if I take an acid plus what we call a metal oxide? Goes to salt plus water. An example of that would be if I take, say, HCl plus Na2O, and I would get 2 NaCl, so I need 2 of these, plus H2O. That's a liquid. So you can remember this if you want. You can say, I know that an acid plus a metal oxide gives me salt plus water. Or what is this really? Yeah, it's just a double displacement reaction, meaning we swapped the hydrogen and the chlorine. We made H2O because we had an H and an O left over, and we made NaCl for our other compound. So really it's just a double displacement reaction. So again, have you learned anything yet? Of course, arguably, I could ask that.
I wasn't going to say anything.
Yes. Okay, I'm waiting. In fact, I'll just do another one on this page since I've got the room. And I'm not, again, doing anything new. What if I take an acid plus a metal carbonate? And the reason they break this down is because a lot of these reactions, we can do to test the strength of acids, or, they're just very specific reactions that occur frequently. For us, we're just going to treat all the acid-base reactions like stuff we already know. So an acid plus a metal carbonate is going to give us salt plus water plus carbon dioxide, so CO2. So if I take, for instance, H2SO4 plus MgCO3, then notice this is really just going to be a double displacement reaction again, but it's a double displacement reaction with a twist in that when we do the reaction we get for our salt MgSO4, but when I swap the other parts I get H2CO3. What do we remember about H2CO3? Yeah, it always decomposes to give H2O plus CO2. It's one of the 3 common decomposition reactions we asked to remember. So the idea is that anytime I react an acid with a carbonate, I automatically make carbonic acid, and that automatically breaks down into H2O plus CO2. So again, just our double displacement reactions from Chapter 8. Sometimes I feel like I'm not teaching anything when I just kind of do the same thing.
Let's just skip this chapter.
Well, let's not go that far.
We've already taken a test on this.
Well, I got to be honest, you should be looking and saying, wow, there's some free points on the test for me.
I am.
And saying, wow, that's going to be good review for the final, because guess what's on the final? Chapter 8 has 5 or 10 reactions you have to complete.
And then 50 you get on the final.
Like 50 or 60. I figure, what the hell? No. That would be an interesting way to write a test, though. Okay, now we're going to, so is everyone okay with reactions, you think? I mean, I can certainly throw more examples up, but carbonic acid, it's one of the 3 common decomposition reactions. I'll get to your question in just a second. So what were the other 2 decompositions? Anytime I make ammonium hydroxide, I know that breaks down into ammonia gas plus H2O liquid. And the other one was H2SO3, always breaks down into SO2 gas plus H2O liquid. So there was 3 of them that you were supposed to memorize as just happening over and over and over again. Haley, did you have a question too?
Yeah, like up there when you put the H2CO3, I thought you only took 1.
Okay, so I did skip a step. So let me show the step I skipped. Sorry, I know I cut you off. Did you have a... So really what she's saying is that I should have said I pair it up like this, right? But I skipped this step where I said we need to balance charges and realize that it really needs to be H2CO3 because of the charges. So you're right, I skipped a step. Okay, the next piece is going to be a little bit of review too, but we're going to branch out and we're going to go deeper into thinking about it, or kind of more in depth, or dive deeper into that subject. So we want to talk about something called electrolytes and non-electrolytes. So what electrolytes are is compounds when dissolved in water conduct electricity. What type of compounds when dissolved in water tend to conduct electricity? This is again review, going all the way back, I think, certainly to chapter 5, and certainly in chapter 6 we talked about these things when we were talking about the two main classes of compounds. Anyone want to throw out a guess?
Electrolyte and
Right, and which one is which? Yeah, these are really talking about things that are mostly ionic compounds. And non-electrolytes are compounds when dissolved in water do not conduct electricity. And so these are what we call, these are generally molecular compounds. Now, of course, there are some ionic compounds when dissolved in water that won't conduct electricity, and there's some molecular compounds that when dissolved in water really will conduct electricity. And so, you know, we're going to kind of go deeper into those definitions and not just say it's ionic and molecular. We're kind of going to add a couple layers to that. And then what we want to understand, though, is the process by which this occurs. So why does this occur? Well, the big reason it occurs is that ionic compounds, if we remember right, gain and lose electrons, right, to complete octets. Whereas molecular compounds have to share electrons to have octets. And this also is going to combine together some information that we already know about how things dissolve, but I'll wait a second because people are still writing. Let's see, anything exciting going on? Brittany, how was your lifeguarding meeting? You got what? Oh. Have you let anyone drown? Well, can't be that bad then.
apparently we're not dressed appropriately to lifeguards.
I would assume you're supposed to wear a swimsuit and be done with it.
Well,
Or
we're not allowed
sweats.
to wear a hoodie if we're cold, apparently.
What? Because it's cold in there if you're not moving around.
I wouldn't wear anything up there that I wouldn't jump in.
Yeah, that's my theory too.
People are gonna say that.
I don't know. I find that people make, I don't know why a hoodie is good or bad, whatever. Sometimes you just got to shrug and go, is it really worth worrying about?
Well, if I wore just my bikini, I bet people wouldn't complain about it, ready to jump in.
It's true. Well, I got to be honest, if you're just standing in the pool, it's not warm. You have to be moving around. Okay, so let's look at how ionic compounds dissolve in water. And I want you to kind of connect this with the things that we've been looking at previously, meaning we've drawn sketches like this, where we might have an ionic compound like KCl here, and we say that, yeah, we know some of it's dissolving in water, and we know some of it's going back out. And we've actually drawn this picture once before. I don't know if we drew it for KCl specifically, but what happens is a K plus ion is going to be surrounded, remember, by water molecules. And why is it surrounded by water molecules? Exactly. So the slightly negative part of a water molecule is attracted to that full positive charge on a K+. So this is an electrostatic attraction. And the technical term for this was ion dipole, because K+ is an ion and water is a molecule that has a dipole on it. And so really what we're looking at again is our intermolecular forces. And then of course the chlorine is the exact opposite in that it has a negative charge, and so what's being attracted to it is the hydrogens from water molecules. And so one of the things that we should realize sort of when we're looking at chemistry is a lot of times we write chemical reactions down, but we never really have these mental pictures necessarily of what's going on. And so if we can have a mental picture of what the molecules really look like in a reaction, then we can gain some deeper insight into what those chemical reactions are telling us or what's really occurring on a small scale. And it goes a step beyond just saying, okay, so I can write the elements down in a chemical formula, I can write the equation out, and I can swap my cations, swap my anions, and things like that. But by gaining or going one level lower than that, looking at what really those molecules look like in solution, what's really going on, that allows us to understand or appreciate more reactions. And it allows us to transition to more difficult things, like for instance, second semester. I shouldn't say it's more difficult. And actually, well, most of you are going to take this class because you have to. What I've noticed about second semester is if you're really good at math, then second semester is a little bit harder, sometimes people say. And if you're really bad at math, second semester is usually a little bit easier, people think. Or if you're just a good student, they're both pretty easy. And if you just suck at life, then they're both pretty hard. So,
I would say if you're a good student, it's still challenging.
I think so too. I think the reason chemistry is challenging is how many people had chemistry in high school? Yeah, not very many. How many people had English every goddamn year in high school and things? How many people had history every goddamn year, or like social studies or psychology? A lot of those classes you just get over and over and over again. No wonder why you're good at English. You talk all the time, and yeah, arguably texting probably makes you worse at English. But did I say that again? Damn it. We should someone take a piece of paper. Someone take a piece of paper and just start keeping track of how many times I use those things, because it's going to kill me. Okay, so that's how and why ionic compounds dissolve in water. So what about molecular compounds? Well, that's the whole point. They don't necessarily dissolve in water too well, right? So for instance, here's a nonpolar molecule. And does it dissolve in water? Not very much. I mean, we can dissolve a small amount of carbon dioxide in water because we can actually form carbonic acid. But not too much of it forms in water because really the only attractive force between them is simply London dispersion forces, which we know are weak. Or if I take something like, say, now see, here's where we have to be very careful. Let's see, how many carbons? I need one more carbon, I need a double bond, and an H, and then an OH, 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 OH. Now, since we're not drawing the real structure and I'm not going and worrying about too many details, this is sugar. What do we know about sugar? It dissolves a lot in water pretty easily, right? So here's a molecular compound that dissolves easily. So what's going on? Because didn't we say that molecular compounds don't dissolve? But they do, right? Why do they dissolve? Why does this dissolve really readily in water? Yeah, so I can have some interactions between H pluses and that, and then maybe I should draw one of these OH bonds out in real life, on paper, whatever. And, you know, this oxygen is attracted to a hydrogen from a water molecule. And so we've got lots of hydrogen bonding and dipole-dipole interactions. But notice, it'll dissolve in water, but it will not conduct electricity because it does not form ions.
What does HB stand for?
Hydrogen bond, or halfback, or I don't know. We got any funny ones for HB? Yeah. And notice that if I look at that previous one, these form ions, therefore conduct electricity. So whether something dissolves or not doesn't necessarily have to do whether it's ionic or molecular, but whether it conducts our electricity does, because it's a question of whether when it dissolves it's forming ions or it's forming molecular compounds.
Why is that one H just chilling kind of by itself?
Which one H? This right here? Well, I drew the OH out, see? To emphasize that all of those OHs can form hydrogen bonds or dipole-dipole interactions.
So they don't form ions?
Yeah, because does not form, oops, yeah, I got a little,
A little sloppy.
I know, that's me.
Well, arguably, when you write that fast.
So we'll define one last thing here today and then be done. I keep saying that, but maybe I'll define more things. Yeah, we'll just go with one more thing. That'll get you through the first half, or 15A homework and the first half of 15B. And remember, we kind of have a shortened cycle for turning things in and getting feedback. I mean, you guys all have tons of time to ask questions, but, you know, the test is Thursday and we kind of can't. No, we're just going to have study days those days and homework days. Or Friday, I don't know, we'll find out.
Did I turn it in last lab?
No, you didn't turn it in, and Miss Gingrich, I don't think, turned it in.
No, are you sure? I'm pretty sure I turned it in.
Maybe you turned it in late. If it is, I think it would be in that pile because that was my stuff people turned in yesterday. I'll look, Jay. Okay, so what we're going to do is we're going to break things apart into three categories. Strong electrolytes, weak electrolytes, and non-electrolytes. And what? No, I didn't hear. Okay. I don't know, we'll see. We'll see. It may or may not. I got to be honest, you should see what they do in the dental hygiene program. They love to cram like 3 tests on the same day. I think they just do it so that the teachers can have an easy day.
Oh yeah, no, we know. We know.
Yeah, I was going to say, you guys probably, well, you all have friends in the program, and so you hear how...
You and Sarah always pair your test up, like on the same.
It's because Sarah's mean. She finds out when I'm having a test and makes her test the same day.
I was
No, because she tells us about ours like 3 weeks.
I'm just teasing, I know. What it is that if you think about it, since we both start at the beginning of the semester and we feel that you should have a test every X amount of material, kind of makes sense that they're a little synchronized. And I usually try to move mine if it really is going to be a problem,
Yeah, you're pretty.
because I don't really care what day it is. Okay, so strong electrolytes break down or are 100% dissociated into ions. It means that if I take a look at a reaction like this, HCl is an example of a strong electrolyte, H plus plus Cl minus, at the end of a dissolving it, I would have 0% HCl and I would have 100% H plus and Cl minus ions. So dissociate is a fancy word for break apart. Yes. So what we're really doing at this point is we're saying that we know that most ionic compounds and a lot of other compounds break apart, and that there is a class of compounds that doesn't break apart. And now we're going to add that middle ground, which is a weak electrolyte, which is things that break apart a little bit, but not a lot. Kind of like ionic, molecular, and what was in the middle? Polar covalent, right? Meaning gain, lose electrons, share electrons equally, share unequally. So weak electrolytes tend to dissociate less than 10%. And so the way we write weak electrolytes, C2H3O2, is we write them as an equilibrium. So notice this is a reaction, or notice the reaction arrow here is simply the forward direction. Here we're writing it as an equilibrium, because really there's substantial amounts of both in there. For instance, there might be 10% that and 90% that. So even though most of them break apart into ions, a good chunk of them do not break apart into ions. Wait. I got the 10 and the 90 here backed up. I was like, that's very strange. So that's 90%, that's 10%. The majority of them aren't broken apart though, right? Just a few. And then, of course, non-electrolytes do not dissociate. So they can dissolve, but for instance, if I take an example of that sugar molecule, you know, if I say it's solid on this side, well, on this side it's still sugar, it's just now aqueous. So it doesn't break apart to form ions. And I guess if I'm being really good about my states, I should put aqueous everywhere. So the biggest difference between a strong, a weak, and a non-electrolyte is simply how much of them break apart into ions. If they completely break apart into ions, we'll label them a strong electrolyte. If they only weakly break apart and only a few of them are actually coming apart in the water solution, then we'll call them weak. And if nothing dissociates, then we'll call it a non-electrolyte. And then what we want to look at is what type of molecules form these things. So, for instance, strong electrolytes are things that are ionic, that are listed as aqueous on our solubility table. Meaning, if it's listed as aqueous in the solubility table, it's almost guaranteed to break 100% into ions. Strong acids also do. And strong bases. And what we mean by strong acids and strong bases is that some acids are strong electrolytes and some acids are weak electrolytes. So I really should throw this on a separate page, but I'm going to cram it in here. If I were you guys, I'd just draw it right under the strong acids part. I just run out of room always. The strong acids are HCl, HBr, HI, and I should point out there's 6 of them. HClO4, H2SO4, and HNO3. I think that's the 6 strong ones. Let me double check, make sure I didn't swap one out of sheer forgetfulness. Well, that'd be silly to actually list them on the homework. Why wouldn't I make you list them on the homework? That's retarded. That's definitely something that should be and is a homework question. Well, I guess I just have them remembered. And then the strong bases are NaOH, KOH, calcium hydroxide, and magnesium hydroxide. So there's 4 strong bases. So when you're studying for the test, you not only have to know the 10 acids and bases, 10 acids that are common, you have to know which ones are strong and which ones are weak. So weak electrolytes are any compound that is basically a weak acid or a weak base. And the way you tell if something's a weak acid or a weak base is it's not a strong acid or a strong base. Meaning, you can memorize the 4 acids that, aren't the 6 strong ones, but really it's easiest to just memorize the 6 and say anything that's not those 6 are weak, right? And so really there's only a few acids and bases you have to memorize as being strong. Everything else, if it has an H plus or no H minus in it, we just label as weak. And then for non-electrolytes, these are usually molecular compounds. They're things that contain basically carbon, hydrogen, oxygen, and nitrogen as the majority of them. But we can also throw in that list that these are anything that's ionic, and a solid technically should be considered a non-electrolyte because a solid doesn't dissolve anyway, right? And so if it's not dissolving, it must be a non-electrolyte or it won't conduct electricity when placed in solution. I think that's where we're going to stop for today. That's a lot of stuff. Hopefully a lot of it is review though. And what this should allow you to do is homework 15A and the front half of 15B. And we'll say, I'm not going to have you turn in 15B only half complete, but so let's make this due Tuesday, and this will end up being due like Wednesday or Tuesday. And here's the key. I'm not going to worry about due dates for this stuff, okay? The idea is that if you want it graded and feedback on it, you have to turn it in before the test, right? And so turn it in. If you want to turn it in before the test, get credit for it, get the feedback, do it. I'm just putting these dates down as probably dates that, that's the last time you can turn it in. Certainly is probably Wednesday, right? And maybe we'll make the test, I don't know, we'll see. There's a 15C and D, but we haven't talked about those yet. So that's it for today. Today's Friday. Have a lovely weekend. Now, I know some people want to set up some times over the weekend to go over stuff, especially in chapters 13 and 14. And frankly, if anyone wants to set up some time, we can set up study gut sessions for the final exam too and start going through what are important. Otherwise, what I normally do is if I gave the test on Thursday, then Friday would just be a study day. And the first part of the final is on Monday. And then what I usually do is Monday afternoon, I'll have a study session for the second half of the final, which is on Tuesday. Or at least set aside some time where this is your last chance to come in and ask any questions. And if people want over the weekend, next weekend, we can also pick 2 times that we want to have, say, some study sessions. So, for this weekend, I'm already booked Friday from, 11-ish to 11:30. That's J. Bradley Jr., JBJ. Does anyone else want to book some time?
I don't know yet. Can I text you? I don't know if I'm open or not.
Well, let's put it this way. How about I'm going to be on campus from, say, 3 o'clock to 5 o'clock on Saturday, and I don't know what time on Sunday. Does that work for most people, 3 to 5 on Saturday?
Text you about later today.
Okay. Remember, if you wait too long, I just go home. And Jess, if you need to borrow my truck to go feed your horses or something while I'm up here, let me know.
Okay.
Did you get them this morning already?
My panic of trying to get people to give me a ride.
Do you have any idea what's wrong with your truck?
He died, but then like it won't hold a charge.